Okay, so today we're looking at something that is gonna totally flip how you think about backend architecture on its head. We're diving deep into an explainer of Chapter 13 from Martin Kleppman and Chris Ricamini's definitive book, Designing Data-Intensive Applications. The chapter is called A Philosophy of Streaming Systems, and honestly, it sets the stage for an absolute paradigm shift. We're talking about moving completely away from those old, rigid ways of managing data and figuring out how modern massive-scale systems actually survive and thrive under pressure. Just picture this for a second. What if your entire backend infrastructure worked exactly like a giant spreadsheet? Really think about how you use a spreadsheet. You pop a formula into one cell, maybe it's summing up a whole column. The second any input in that column changes, bam, the result cell is automatically and instantly recalculated. You don't have to hit a refresh button or manually tell it to update, the data just flows. Well, that's the brilliant metaphor at the heart of today's explainer. We're going to see exactly how to design backend systems where data flows dynamically, reliably, and automatically, just like those spreadsheet cells. All right, let's take a quick look at our roadmap. First, we'll tackle the data integration challenge, then unbundling the database. After that, we're covering designing around data flow, aiming for correctness, timeliness versus integrity, and finally, trust but verify. It's going to be a great ride from basic data integration all the way to verifiable asynchronous distributed systems. Section 1. The Data Integration Challenge, Bridging Specialized Tools. Look, we just have to face facts here. No single database on Earth can do everything perfectly. You might have an operational database handling user transactions, right? But you also absolutely need a full-text search index, and maybe a caching layer, and definitely a data warehouse for analytics. And that brings us to this crucial concept, derived data. Derived data is technically redundant. It's duplicating information that already lives in your primary system of record, but you literally have to have it. By maintaining derived datasets, like your caches and search indexes, you're basically looking at one single system of record from a bunch of different, highly optimized angles. The real headache, though, is this. When the primary system changes, how on earth do we keep all this derived data perfectly in sync? Well, there's this absolutely wild mathematical relationship that solves this exact problem. Check this out. State is simply the integral of streams over time, and streams are the derivative of state. Let's break that down into plain English. A stream is just an append-only log of immutable events, things that have already happened, like adding an item to a shopping cart. State, on the other hand, is what you get when you apply all those events together, like the current total price in that cart. They're literally two sides of the exact same coin. If you store a log of every single event that ever happened, your state becomes 100% reproducible. You can derive any view you want just by hitting play on that log. So to actually process these logs and keep our derived data fresh, we basically rely on two main methods, batch and stream processing. Batch processing handles bounded, finite chunks of data. It is fantastic for taking massive amounts of accumulated historical data and completely reprocessing it to build entirely new views. Stream processing is the flip side. It deals with unbounded, never-ending data streams. It processes events the second they happen, which keeps your derived views updated with incredibly low delay. But here's the cool secret about both of them. They're really just tools for running deterministic derivation functions. They take inputs, process them, and push state changes into your derived systems. They're basically the engines powering that giant spreadsheet we talked about. Which brings us to Section 2, Unbundling the Database, the Unix Philosophy for Data. If you think about what a traditional integrated database does behind the scenes, it's super monolithic. When you write a row to a table, the database uses a synchronous transaction to update all its internal indexes. Everything happens at once, tightly coupled together. But the authors of this chapter propose something pretty radical: unbundled databases. What if we basically rip those internal index maintenance features right out of the database? Instead of all that tight coupling, we go for loose coupling. We use asynchronous event logs, think tools like Apache Kafka, to connect composable storage systems. The absolute beauty of this unbundled approach is fault containment. Think about it. In a synchronous transaction, if one tiny part fails, the whole thing aborts. The fault is amplified. But with a log-based asynchronous setup, if your search index crashes, your primary database just keeps right on taking orders. Instead of you waking up to a 3 a.m. pager alert, the log just buffers the messages. When the search index finally comes back online, it just catches up. The fault is totally contained. Moving right along to Section 3, Designing Around Data Flow, from Core to User Interface. When you start structuring your systems around this data flow concept, you're essentially dividing the world into two paths. Path 1 is the write path. Whenever data gets written, it flows through a stream processor, updating all the necessary derived datasets, the caches, the search indexes, maybe some machine learning models. It's a continuous pipeline of state changes. Path 2 is the read path. When a user actually queries the system, they aren't scanning that massive event log. They are doing a fast, random access query against the highly optimized derived store. Usually, the data store sits right in the middle as the boundary between these two paths. But the author suggests something really cool here. What if we push this right path all the way out to the end user's device? Instead of a web browser constantly polling the server asking, hey, any updates, the server just actively streams state changes directly into a client-side event pipeline. Your UI becomes unbelievably responsive because it's reacting to a live stream of data flow, again, exactly like a cell in our spreadsheet. Section 4, aiming for correctness beyond distributed transactions. So here's the catch, right? If we're ditching synchronous transactions for asynchronous event streams, how on earth do we know our data isn't getting totally garbled? The answer actually dates all the way back to a 1984 paper by Saltzer, Reed, and Clark about the end-to-end argument. They wrote that correct implementation can only happen with the knowledge and help of the application at the endpoints. In plain English, a fancy, highly transactional database cannot save you from your own application's bugs. If your app decides to write garbage data, the database will happily wrap that garbage in a pristine, serializable transaction. True correctness has to be an end-to-end responsibility. Okay, so how do we actually enforce rules and constraints without all that synchronous overhead dragging us down? It boils down to 3 actionable steps. First, make sure you represent your write operation as a single atomic message in an append-only log. Second, rely on deterministic derivation functions to build all your other state updates from that single message. That means if you run the exact same message through the function, you get the exact same state update every single time. No surprises. Third, and this one's a lifesaver, pass an end-to-end client request ID through all levels of your processing. This lets the system easily suppress duplicates. So if a network blip accidentally sends a message twice, the system spots the ID and just ignores the second one. This setup lets you scale massively while keeping your data fiercely accurate. Next up, Section 5, timeliness versus integrity, relaxing the rules safely. We throw around the word consistency all the time in software engineering, but honestly, it's dangerously overloaded. To really master streaming systems, we need to split it into 2 totally distinct concepts: timeliness and integrity. Timeliness just means ensuring a user observes the system in an up-to-date state. If a system is purely asynchronous, a user might load a page and see a slightly stale value. Integrity, on the other hand, is the absolute absence of data corruption or data loss. The crucial takeaway here is this: a lack of timeliness is just a temporary annoyance. If you wait 2 seconds and hit refresh, the data shows up. But a violation of integrity? That is a permanent catastrophe. If the data is gone, waiting around isn't going to bring it back. Think about it like checking your banking app right after you buy a coffee. That transaction probably isn't showing up yet. The system lacks timeliness. But are you freaking out? No, of course not. You know it takes a day or so to clear. But if your statement balance doesn't mathematically add up, or if the coffee shop literally never gets your money, that is an integrity violation. That's the disaster scenario. Streaming systems and unbundled databases are so powerful precisely because they understand this difference. They safely sacrifice a little bit of timeliness to gain absolutely incredible performance, while rigorously, mathematically, protecting the integrity of your data. Which brings us to our final section, Section 6, Trust but Verify, the ultimate fallback. We just have to accept that bugs happen. Hardware fails. In complex systems, data corruption is eventually going to happen. And that is exactly why we rely on auditing. Auditing is explicitly checking the integrity of your data pipelines end to end so you can spot corruption early and stop it from doing downstream damage. Now remember our giant spreadsheet. Remember our append-only log of immutable events? Because unbundled databases use those deterministic data flows, we get this incredible superpower. We can constantly audit our systems. We can literally take our immutable log, run it through a parallel verification pipeline in the background, and make sure the derived state perfectly matches our primary systems. If a rogue bug ever corrupts our search index, we don't lose the data. We just fix the bug, wipe the index, and replay that immutable log from the beginning. It is literally like time travel debugging for your entire backend. So I want to leave you with this one final thought to chew on. Knowing that you can compose systems asynchronously, contain faults locally, build dynamic spreadsheet-like data flows, and guarantee true end-to-end integrity, are you still trying to build a monolithic database in a streaming world? It really might be time to rethink your architecture, unbundle that data, and fully embrace the asynchronous data flow. Thank you so much for hanging out with me for this explainer on Chapter 13. I really hope this sparked your curiosity and gave you a powerful new mental model for your next big system design. Until next time, keep exploring and keep learning.